Hi everyone, welcome back. I'm just going to do chapter 18 this week. I'm going to then do next week a little bit about water pollution and water, and then I'll wrap it up with climate change. I feel like putting climate change and air pollution in the same lecture is a little overwhelming for the week. Please let me know if you're having issues with any of the labs or anything. That last lab that's coming up, the one from the kit, the bioremediation, please read the instructions carefully. I put some notes at the top. My kit was missing water, which I don't think it matters. You can use regular water with it, but it asked for distilled water. If it's really worrying you and you're on campus, I'll grab you a little cup if you stop by my office or you want to come in and ask for it. But otherwise, I think you're fine with what the kit has. Just be aware that also takes a little bit of time. So does the final nature journal. You can start that now. I've tried to make everything so that it shows up for you, but take a look, go through that stuff. Even more importantly than the lecture right now, figure out what you need to do over the next couple days. That's also your discussion for this week, to figure out what are you supposed to do for the last few weeks and get a handle on it. Because wow, this semester ends so fast every year. I always try to right now rein it in and figure out what's going to happen. So I'm going to help you do that too. And then I'm going to get started. I think I'm going to break this in half, a little bit about air pollution and then a little bit about how we control for air pollution. So let's start with a case study about the Great Fog of London. This is different. Your book talks about LA. I'm happy for you to read that and do this one. They're very similar situations in slightly different cities. Both LA and London sit in a basin. There's a river running through London, the Thames. And London, when it gets very cold, sometimes gets air, like LA, trapped down over the city. In 1952, on December the 5th, the air was like really cold for several days, and people had been burning pretty regularly something called dirty coal. Coal, as you know, is created from compressed plant material that's been squished for a really long period of time, and there's different levels of coal that burn at different cleanliness. This is, I pointed out in the last geology lecture, what they were burning was that really dirty coal, and it gives off a lot of particulates, a lot of sulfur dioxides, and a lot of other particles into the atmosphere. And because of the weather event that was happening at the time, none of that went anywhere. It didn't blow away. It sat down on London. So it started out a little bit smoggy, and smoggy is smoke. It's not fog. It's toxins in the air. As that smog began to roll in, it started to turn yellowish black. And obviously these photos are in black and white, but tint them yellow in your head. That cold weather that was sitting down on the city is called a temperature inversion. When a temperature inversion happens, the warm air sits on top and the cold air sits on the bottom. And because they're reversed, right, it's not the cold air doesn't normally rise. It gets trapped by the hot air on the top. When that happens, it keeps the air from moving at all, and the pollution sits in a place where people are living their everyday life. Okay, so according to the Metropolitan Office, which is the police department for the entirety of Britain, when they recorded the types of pollutions that were in the city during those 5 days, there were 1,000 tons of smoke particles, 140 tons of hydrochloric acid. Yeah, that's hydrochloric acid, like what you dissolve meat in your stomach with. Fluorine compounds, 14 tons, and 370 tons of sulfur dioxide, which in the presence of water, so we take sulfur dioxide and we add it to H2O, converts into H2SO4. That sulfuric acid, and if you think hydrochloric acid in your lungs is bad, sulfuric acid is worse. The Air Pollution Committee put together these graphs and before computers, so it's all hand-drawn. In this period of time, we can see the temperature stayed low, the amount of poison, smoke, and sulfur dioxides rose and stayed high, and we see an accompanying really high rate of death. By the time the 4 or 5 days later that smoke actually lifted, 2,000 people were dead, mainly from heart and lung complications. But that was not the end of it. We think, looking back on this, that over 100,000 people actually suffered long-term health effects, and 12,000 people died as a direct outcome of living in London and going outside because of the pollution that was sitting on the city. Air pollution is incredibly dangerous for us. There's a reason why your phone, everybody's phone has a weather app on it that monitors air pollution, and it sends you a notification if the air pollution is too bad for you to be outside. You get notifications that say things like it's unsafe for vulnerable people, unsafe for everybody. A couple years ago, we had a lot of fires in Canada that burned down into New Jersey. The smoke blew down here, and we were sealing up our house. When we do that, that's because the particles in the air are dangerous to our lungs or small enough that they can actually get into our circulatory system. The small particles that are associated with breathing them into your lungs, what's really dangerous about them is if they can move from your lungs, alveoli, the sacs in your lungs, into your circulatory system, and now they're in your blood. And as they move around your body, they damage your tissues, they block arteries, they cause long-term stress and inflammation inside of your body. Everything from aggravating lung diseases that were already there to causing asthma to develop in children and adults, bronchitis, which is where your bronchial tubes in your lungs are inflamed, and they can stay chronically inflamed. These can lead to heart attacks and cardiovascular problems. They can lead to strokes later on. In the U.S., we estimate about 70,000 people, mostly older people, every year die prematurely due to consequences of air pollution. It seems like it's just air, but when you're breathing that in, you're doing intense damage to your body. The atmosphere that surrounds us all the time is always changing. And when the pollutants sit in our lungs, those pollutants can be brought in as the air around us moves. I do want to highlight a couple different things about weather and climate as we go through, and then we'll come back in the final lectures. I feel like I've talked about some of this as we've gone along. Worst case, I want to talk about it again. We've talked about weather versus climate. I feel like we've done this again, but it's really worth mentioning on a lot of levels that the weather is short-lived. It is what we are doing today. Today, it's actually quite pleasant out from where I am. It's, I don't know what it is. It's Sunday, the 19th of April, where I'm sitting. It's kind of a nice day. 3 days ago, it was kind of hot. The weather changed really rapidly. Our climate is our pattern of temperature and precipitation. Our climate does not change rapidly. I think my head is over the word climate there. Our climate is the long-term prevailing conditions in a region. It determines our biome. Our climate right here is temperate deciduous forest, or temperate climate, where it gets hot in the summer and cold in the winter, and kind of fall and spring are sort of nice. The atmosphere is all of the air from the ground all the way up into outer space. We divide our atmosphere into several zones, kind of like we divide the layers of planet Earth into several zones. The zone closest to us is the troposphere. That's where we live. So if you're going to draw yourself, you're probably right down there. I'll put you at the base of Everest, your Everest base camp. Congratulations, you got there. You're still in the troposphere. Even if you climb all the way up to the top of Everest, you're still in the troposphere. This is where we live. This is where there is wind. But outside of that, above us, there is the stratosphere. Above the stratosphere is the mesosphere. And then still in our atmosphere, the thermosphere protects us from outer space. The troposphere is where we live right now. And I think unless you have been to space, you have never left this and might never leave the troposphere in your lifetime. This is the outer edge of where we normally go. Mount Everest is about 8,000 meters. That's really high. 8,000 kilometers high, or 8 kilometers high. That's about the edge where it is of the troposphere. In other parts of the planet, it goes up to 18 kilometers thick. That's where there's breathable, or at least wind and air molecules moving around. You know, as you climb higher and higher up a mountain, that the level of oxygen that you have access to is less and less. That's because you climb up, the pressure of the air above you becomes less and less. There's less air above you. So those molecules of oxygen are moving further and further apart. They're less smushed close together. And so each breath, you actually draw in fewer oxygen molecules. So the air gets thin and hard to breathe, but there's still moving molecules around in it. Warm air rises within the troposphere. It mixes with the cold air that's up higher in the troposphere, and then it flows around in currents and wind patterns and convection patterns. When you get to the end, the highest point where the wind goes, right above that is the tropopause. That's the period, the place where the wind stops and there's no more air mixing. The tropopause separates the troposphere, the sphere of where we live, from the stratosphere, the protective layer that protects us from a lot of UV damage. The stratosphere is from the tropopause up to about 50 kilometers. It's about 33 miles high. Again, you have probably never been here. This is much higher than airplanes fly. There's almost no water, but there is ozone. Ozone is O3, here's a molecular drawing here, and ozone's biggest advantage to us in the stratosphere is that it reflects UV light back out to space. It is a protective coating around the planet that protects us from the sun's damage. The sun is awesome and it's the source of all our energy, but it is also a source of damage to our DNA, and it's cooking us. We need it to be sort of the optimal living conditions. The ozone layer in the stratosphere protects us against damage from the sun. There's a lot less movement and mixing of air up there. If particles make it up to the stratosphere, they stay in the stratosphere for a really long time. Say, for example, something made its way up there that damaged ozone, it would stay there for a really long time. The mesosphere is above the stratosphere. This is where meteors burn up and you see them flaming. This is probably where you see the little shooting stars. A couple weeks ago, there were a lot of shooting stars and meteorites coming down. There were a couple that were seen in New Jersey. We passed through a group of particles that burn up in the mesosphere around us. They don't usually reach the stratosphere or the troposphere. I don't have a lot to say about this. From our point of view, we might have some little bit of interaction with the mesosphere, but for this class, no. And then the thermosphere, this is space, but not quite. It's the layer that protects us from the really outer space. It's the last layer of the planet Earth. It is full of ionized gases. These gases are heated by solar and cosmic radiation. This is where the aurora is. This is the aurora in New Jersey 2 years ago, maybe 3 years ago. It's obviously filtered through my camera so you could see a little bit of the colors. But if you've ever seen the aurora, it looks different colors based on the angle you are looking at the ionized gases reflecting light. And it causes them to glow. This is the Bifrost to the, if you're going to Valhalla, you need to take the Bifrost. It's the aurora, and it is sitting in the thermosphere. Above that, outer space, the exosphere. Exo means outside the sphere. And most people don't get to go there. Reminder that the solar energy reaching the Earth is mostly near infrared. We have the colors that we see, the visible spectrum, but a lot of the dangerous energy waves that are coming at us are reflected by our atmosphere. Our living things and our planet and our ocean absorb some of the heat. The ocean acts as a sink for a lot of the heat that strikes our planet. Plants photosynthesize and take in some of that energy. Some of it's bounced off of the surface, and we'll talk about this in the last couple lectures, but some of that energy is bounced off of the surface of the planet up, and it hits little tiny particles in the atmosphere and bounces back down to us. That's the greenhouse effect. This is awesome. It keeps us alive. If you've ever been in Dr. Flisser's greenhouse, you know that place is really, really hot. Space is really, really cold. What happens is that little bit of trapped heat gets bounced around and stays and keeps it at a living temperature so that we can live here. I want to stress here the greenhouse effect is a good thing. It keeps us alive. It just can get out of hand. The greenhouse effect on Venus is really, really powerful. It's a little bit too hot for us to do well there. Greenhouse gases, things like carbon dioxide, water vapor, nitrous oxides, and I'll do this here. I'll put carbon dioxide, water vapor, nitrous oxides. There's several, so we're going to write it as NOx, NO, and some amount of oxygen, methane, and other substances bounce the rays that are bounced off the Earth back at us and keep us warm. These are supposed to be in the atmosphere. Air pollution adds particles to the atmosphere that aren't normally there, but this can be 100% natural. Things like volcanoes, this is a haboob, it's a big dust storm. Vegetation too, I don't know if you've been outside recently, but the pollinating is happening. That is all air pollution and can absolutely interfere with our breathing. It can get into your circulatory system if it's small enough, but these are natural occurrences. 2/3 of the methane in the air is caused by bacteria doing bacteria stuff. So this is supposed to be happening, or I mean, maybe it's not awesome for us all the time, but this is a natural part of the Earth's cycle of how the system stays in balance. Human sources of air pollution are caused when we break down molecules that have been stored for a long time in the Earth's crust or somewhere else, and we release them. We release particles that are completely natural and part of Earth's cycle, but higher amounts than we actually expect. These human sources of air pollution are anthropogenic. Anthro means people, like anthropology means people, the study of people. Anthropogenic means it's man-made. Anthropogenic pollution is really, really bad for us. What happens is we burn fuel sources, as we do manufacturing, mining, all of those things are released into the atmosphere at levels that can sometimes be dangerous for all living things. Sulfur dioxides, if you remember from London, I don't know if you've been to London, when I was talking about London, can turn into H2SO4. But it also forms particles in the atmosphere that reflect light differently and heat. Nitrous oxides, carbon monoxide, I want to especially talk about that because it's incredibly dangerous for us to breathe that in. Ozone, good, bad relationship with that. As long as it's in the stratosphere, we're happy with it. Lead, which I can't think of any good reason we need to breathe that in. And particles or particulates, the smaller they are, the more dangerous they are. And I actually pulled this from another textbook. I really like the breakdown here of where all of these particles come from. Stationary combustion means burning fuels in a specific location, so manufacturing, as opposed to transportation. This is coming from cars. In New Jersey, and this was the most recent data I could find, in New Jersey, we consistently fail to meet at least 1 to 2 of the regulations for our Clean Air Act. So the Clean Air Act has been updated several times. I'll talk about it at the end of the lecture, but it regulates how much particulate and pollution can be in our atmosphere. If you zoom in on us right here, you can see that we recently failed. This is the most recent data I have, so 2017. We've recently failed at least 2 of them. One of those is consistently ozone. Ozone is something you can smell. I don't know, you can kind of smell it this week or last week in the hallway when they were working on the heat system in Halpern Hall. That kind of crisp, tangy smell in the air. But often in the summer, because of the way that the plants along the Delaware River manufacture, you can also smell ozone when you get up real early and go for a run. It's not great that you can smell it. It's not going to kill you right away, but it means there's heavier amount of trapped ozone at breathing level rather than going back up into the higher atmosphere. And they do release it from the plants early in the morning in the hope that that morning air will carry it up into the stratosphere. I want to look at a variety of different pollution particles and locations where they come from. Primary pollutants are released directly from the source. We can point at them and say they are coming from that place. but also they are released in their final form where they are dangerous from the moment they're released. Secondary pollutants are much harder for us to deal with. These are pollutants that are released in a form that maybe isn't so bad, but when they combine with particles like water and other things in the atmosphere, they become something more hazardous. So they seem okay until they actually get out in the world. And when we run tests on pollutants and other things, and even when we run tests in medical situations, a lot of times we have to consider a compound or a chemical in what it does in the lab, but what it also does in a human body. And this is similar, what it does in the lab versus what it does in the real moving atmosphere. Fugitive emissions come from places that are not smokestacks. Things like mines are a big source of fugitive air pollution emissions. Digging creates a lot of dust that spews up and it travels around, and we'll look at how it moves around the planet. That can be something that people end up breathing in miles or hundreds of thousands of miles away. It's very listy. I want to list some of the primary pollutants we're going to talk about and the major outdoor pollutants. I actually picked the ones that I think are most important. This is not just a list of chemicals for you. This is a list of chemicals that you actually need to know in order to understand air pollution. I want to talk about sulfur dioxide. It comes from sea spray, from volcanoes, and from burning organic compounds. We make it during fossil fuel combustion. So when we burn petroleum products, when we do manufacturing, when you drive, when you burn anything for coal or oil. This was the problem in London, is they were burning a form of coal that burned dirty. A lot of extra particles and a lot of extra sulfur dioxides were given off in that. And again, when sulfur dioxide mixes with water, it's corrosive, which means it breaks things down, and it becomes acid. This is a major contributor to acid rain. Acid rain is when the rain becomes, and you all have been testing it last week and this week, depending on how that experiment went good for you. How did your plants grow in vinegar? In my experience, they kind of disintegrate it. Like my lettuce seeds disintegrate it in vinegar. That's not great. Acid rain can get to be the pH in vinegar. It can be a pH of 3. That's not great for anybody. Frogs, plants, or any living thing. Nitrogen oxide or nitrous oxides are reactive gases that are formed when nitrogen is heated really high. 650 degrees Celsius, that's manufacturing, that's not everyday life. It is a massive greenhouse gas, and it's also something that contributes to acid rain. When we put it with water, it becomes acidic. This is basically us, whereas sulfur dioxides can come from volcanoes and other things. Nitrogen oxides are us. We're increasing those levels of burning nitrogen-containing compounds. Carbon monoxide. This is a gas. It is toxic, odorless, and it sits at breathing level when it sits in the atmosphere. It is caused by not completely burning the fuel off. It's produced by cars and trucks. When you breathe it in, it binds to the hemoglobin in your blood that is trying to bind to oxygen, and it prevents you from you're breathing, but it prevents you from respirating. So you're no longer doing cell respiration properly. If you kind of flash back to first year bio, the role of oxygen in cell respiration is to pull the electrons down the electron transport chain so that you can make ATP. Yeah, you can't do that with carbon monoxide. It doesn't do that. This is a thing that you should have a monitor in your house. Everyone on every floor of their home should have a carbon monoxide detector. It is an odorless, deadly gas that can build up in your home if you have a bad heater. Or in one of the most tragic cases in the last 10 years, somebody leaves their truck running in a motel overnight, and it blows all of that exhaust into the motel rooms, and everybody in the motel dies. And you would just never wake up. You should have a monitor in your house. Ozone and other photochemical, photo means that they react with light and break down, photochemical oxidants. Oxidants are oxidizing, they break things down. Another word for this would be like to rust. The ozone layer in the stratosphere basically protects us from excess UV light. so that the light coming through is not right away ready to burn us. You got to stand out there for a little bit. But in the troposphere where we live, ozone is dangerous for us. It smells sterile. I don't know how to explain when you smell it, you know what it is. It smells like the air has been sterilized. It's maybe doesn't look like anything, but you can smell that you shouldn't be taking deep breaths. It damages vegetation, it damages buildings, and it's terrible to breathe in. Finally, lead. Lead has probably not been as big of an issue in your lifetime as it was when I was small and growing up in my parents' lifetime. Lead used to be more abundant in the atmosphere because it was given off burning fossil fuels that were used in cars. When you buy gasoline now, it is unleaded. For a long time, gasoline had lead added into it and kept in it if it was the type of gasoline that has lead already in it, because it stopped engine knocks. But it interferes with neurological development and makes people angry and stupid, which is exactly what it does. Lead poisoning is one of the reasons we think that the Roman Empire kind of fell apart. Lead poisoning in our, the last 2 or 3 generations has been an issue with cognitive decline probably, but also it's a poisonous metal that interferes with the development of your brain. It's a neurotoxin, meaning it is toxic to your nerves. It was banned, and I have some charts for you. It was banned. When it was banned, children stopped having as high of levels, and we've actually seen a corresponding increase in IQs. Here, this is old, so this is 2015 is the date of this chart. So people that were 40-ish, 40, 50 in 2015, they're 50, 60 now. We're exposed to a lot of lead in the atmosphere. This is definitely tied to, so at the risk of going off the rails in this is definitely tied to more aggressive behavior. We see if you delay this chart by about 18 years and look at violent crime, you see that by the time these people get to be about 18, we see a rise in violent crime. The drop in crime, we think, is partially due to the fact that we don't have this pollutant messing with people's brain development. So these people would be 60-something now. Your understanding of that may vary based on who you know. Particles in the atmosphere reflect light, the sun's energy back out to space, but they also trap heat and light, trap heat here, not light. They reflect heat out to outer space and trap heat here. Those particles are aerosols, tiny particles that can aerosolize or end up in the air, suspend in the atmosphere. When you breathe them in, they become the primary cause of things like lung cancer. Lung cancer today is primarily found in people who did not smoke. Smoking is no longer tied to lung cancer the way it is. I'm not saying that you should smoke. Smoking definitely leads to cancer. It's just fewer and fewer people smoke, and now the rise of lung cancer is due to particles in the atmosphere and possibly other issues. Possibly the fact that we're breathing in higher levels of particulates in the atmosphere. I'm going the wrong way. In the 1980s, when people were monitoring the atmosphere, they noticed that over Antarctica, depending on the season, particularly in the winter, there was a really big hole in the stratosphere of ozone. That ozone protects us from being cooked by the sun, so it was a problem. And what was found is that chlorofluorocarbons, or CFCs, were going up into the stratosphere and damaging the ozone, and in fact, eating a hole in the ozone layer. On the troposphere at ground level, ozone is a pollutant. But in the stratosphere, it keeps us safe. If about 1% loss of the ozone in the atmosphere, we see a huge rise in skin cancers. You still should wear sunscreen. We have been able to address this somewhat, but this is a massive loss of our protective coating. This also ties in, if we're missing that protection from excess UV light, that UV light also damages plants, it damages animals, and they really don't have a lot of access to sunscreen at the store, so they're more likely to be damaged, and UV light directly damages your DNA and your DNA repair systems. If you have anybody you know who was a teenager in the 80s, they will tell you about Aquanet and how you made your hair go straight up. Aquanet was like a force of nature. It was also propelled by CFCs. The Montreal Protocol was enacted in 1987. It was one of the most successful worldwide collaborative programs that humans had ever done. We agreed worldwide to switch from CFCs into an alternative propellant, an HCFC. So this is what we use now. These do not damage the ozone layer. They release less chlorine, so it doesn't bind to the ozone at all, and the ozone layer has been repairing itself. According to your textbook, it talks about the fact that it might be completely repaired by 2050. The most recent data, like this year, suggests that we might actually, by the time you're about 30, have completely repaired the ozone hole. Not only do HCFCs not damage the ozone layer, but they actually release fewer pollutants into the atmosphere. So this is like a win-win-win-win-win. It shows how we can all work together, but it also, these CFCs were not heavily invested into generations of people's lives. It's a little bit different when we talk about burning gasoline or petroleum. That's kind of integrated in our society, and there's a lot of big money involved. There was a reasonable alternative and a lot of motivation to get rid of CFCs. And I think it may be in your living memory you don't remember them being available at all, which is a good thing. Kind of like you probably don't remember lead in the gasoline either. Reducing outdoor pollution can just happen. Gravity allows the particles to fall down. Rain and snow, rain and snow, when they come, it cleans the air. Salty sea spray from the ocean is ionized. It traps those particles and it brings it back into the cycles in the ocean. Wind blows it away. And that's what the people of London were desperately waiting for, because they were stuck in a trap where a temperature inversion was keeping the poison really close to where they breathed. Some chemical reactions also break down the pollutants and turn them into less harmful substances so that they don't hurt you. Increasing outdoor pollution. So this is the EPA's plan to decrease outdoor pollution. And it has a really nice set of explanations of how pollution in the air accumulates and what we can do every day to target that in our lives to get rid of it. Just like living in an urban area, and the breakdown of urban environments traps particles in your breathing space. Hills and mountains do the same thing. So we get trapped by these big structures or big pieces of earth, and it creates a well where particles sit and don't move around as much. One of the things in Boulder, Colorado, that they have to deal with all the time is Boulder sits in a valley that is surrounded by really big mountains, and there's a lot of wildfires on the west coast. Those wildfires blow smoke into Boulder, and the smoke doesn't leave. And it looks pretty. It looks so pretty and blue, but what's really happening is all of those particles are sitting around, and people are breathing really bad air days, especially if it gets really hot, and it does. And some plants and certain trees have volatile organic chemicals, or VOC emissions, that are dangerous for us. I want to just, on the next two slides, talk about grasshopper effect and temperature inversions finally again, to talk about some of the larger effects that actually increase your air pollution, where you might not actually be creating it, but it's coming at you from a different place. Grasshopper transport, or grasshopper effect, is not at all like being a grasshopper. What happens is because of the way the world spins and the wind blows, when we create pollutants at the equator, they blow north and they move and they kind of jump up into the upper atmosphere, and then they come back down and they drop down on places really far away. We can build up poisons in the Arctic, where obviously nobody's doing a lot of manufacturing in the Arctic, but all of the manufacturing that's happening in the northern hemisphere jumps all the way to the north and causes pollutants to build up in polar bears. The polar bears are really far away in a pretty clean environment, but our grasshoppering effect of pollution is raining down on them. This also means that pollutants made in one country can rain down on another, which means this is a multinational problem. It's a big problem between the northern United States and Canada, because we do a lot of manufacturing in the US at the northern edge, and then that blows up north into Canada and poisons their forests. Most of the people in Canada live on the southern edge, same thing. All that manufacturing is happening in the same region, and the northern part of Canada, where very few people live, is then under a lot of pollutants. We see the same thing across northern Europe, across northern Russia, where manufacturing in areas where it's more urban and people live is damaging the sort of pristine northern areas that you would think would be protected from some of human pollution. Temperature inversions, this is what happened in London, but it's also what happens in LA, it is what happens in Boulder, it happens in Philadelphia. There's temperature inversions when it takes advantage of either topology or trapped areas where cities sit in valleys. And we tend to build our cities in valleys because we like to build our cities by rivers for easy transport. When you get stuck with that cool air sitting down, a layer of warm air sets on top of it and traps it. Or we can have, and then it traps all of the pollution in this area and cycles it round and round and accumulates it as people breathe. If we build our cities in places where we have places that the wind can blow through them, we see less of a problem. We don't see temperature inversions in San Francisco because the Pacific winds are often blowing. They're always blowing across San Francisco. With that, I'll take a break. I have a little bit more for you. I want to talk about air pollution indoors and outdoors. We've been talked about in your house. I want to talk about the Clean Air Acts and talk about some of the actual contributors to acid rain. Take a break and I guess go outside and take a deep breath because the air is beautiful today, and at least it will be for the rest of the week. And enjoy the fact that the rain is probably, as you're watching this, knocking all of that pollutant and pollen down. And I'll see you in a little bit.